Okay, let's start with last time. Do we have any questions from last time?
Sir, I was checking my missed class and I actually have two questions on eigenstate and something called Hermitian operator acting on psi and giving an eigen value of something. That and another question is what is degeneracy?
Yes, please. Yeah, so yeah, ask the questions. Those are good questions. So what is the first one? Is that what is an eigenstate, is it?
Yeah. You showed an equation operator acting on psi gives O ij like momentum I energy eigenstate operator. This thing is the first question.
Okay, so the question is what does it mean?
Yes,
Okay,
what does
so what is
this
an
eigenstate
yeah,
mean and how does it work?
okay. So, let's think of operators, okay? So what are operators? The definition of an operator. So we are looking at a linear operator. Those are the operators we're interested in quantum mechanics. Um, can you guys see that I'm writing? Yeah, it's probably there's a
Yes, sir.
lag. Okay, so they're linear operators. What are linear operators? What they do is that they map us from the state of space. So let's call that space of states. Let's call it H. H stands for Hilbert space, okay? So this is basically all the psi's are in this space, okay? So what linear operators do is that they map you from this space to itself, okay? So, so if L is a linear operator, then L acting on psi, where psi is an element of H, gives you another wave function phi. So, both psi and phi are in my space of states. Okay.
Yes, sir.
So, yeah. And linearity means that if I have L acting on a linear combination of states, say alpha is a constant, psi is a state, beta is a complex constant, and phi is another state. So this is a state in my Hilbert space H, right? Now, the linear operator acting on this linear combination would be the same as if you act by the linear operator on psi, and if you act with the linear operator on phi, and if you multiply that by alpha, and you multiply the latter by beta, and you add them, okay? So this is what linearity means, okay? Okay. Now, for every linear operator, uh, for every linear operators, you know, there exists at least one, say, state such that when L acts on that state, we get that state back. Okay. So, so for example, L can act on say psi of alpha. Alpha is just an index here. We get back Let's not put alpha because let's put just I, okay? So we get back that state itself, okay? Is that clear?
Yes, sir.
So
I mean, the operator doesn't change anything of the state.
it rescales it. So if I were to write the, if I remove the proportionality sign, it's going to give me some number, say alpha I. There's a constant of proportionality, okay?
Yes, sir, got it.
Yeah. So this state, psi I, is called an eigenstate. Eigen is a German for characteristic, okay? Eigenstate of L, belonging to the eigenvalue alpha I, okay? So this is called an eigenstate, and the constant of proportionality is called an eigenvalue, okay? So in some sense, it's really the eigenvalues and the eigenstate that characterize an operator, okay? It's the values of the eigenvalues. This is known as the eigenvalue spectrum, okay? It's the values of the eigenvalues and the eigenfunctions or the eigenstates and the, I should say, and the corresponding, eigenvalues, sorry, eigenstates, I should say, eigen functions or states, they're the same. Eigenfunctions or eigenstates that characterize the operator. Okay. All right. So those are the definitions. Now, an important result. Important result is if an operator is Hermitian, then its eigenvalues are real numbers, okay? And in quantum mechanics, so in quantum mechanics, observables are represented by Hermitian. Actually, it's more restrictive than that. Self-adjoint operators. And the result of a measurement of an observable always yields a possible eigenvalue of that operator. Okay? So, for example, if I have H is the Hamiltonian operator, and it represents the total energy, okay? So if I have H acting on psi n, En of psi n, then Ens are the possible energies, okay, of the system. So if you measure the energy, suppose I give you a state psi, and you measure the energy, then you must obtain one of the values En. You're not going to obtain any other values, okay? If you
Sorry,
copies of psi,
sorry. Is it like if the operator is
suppose you have 100 copies. Sorry, Farhan, can you repeat the question?
okay, sir? I guess there was internet disconnection. If I represent the operator as a matrix, then acting the operator on a psi gives the eigenvalue of the operator in front of the psi. Is that correct?
Yes, only if the psi is an eigenfunction. If the psi is not an eigenfunction, you won't get that.
Okay, sir, understood.
Yeah. So for example, if psi is some random state and I take 100 copies of psi and I measure the, I measure energy of psi, 100 times, then I'm not going to be able to get, in principle, I won't get the same value all the time. What I'll get is, I will get some distribution of values of En, and, and it might be, and then I might have a histogram, okay? Okay. And that will give me the average of the energy, right? Okay. If psi was one of the eigenstates, then 100 times, if I measure, I'll get the same eigenvalue Ei. But for general psi, can be written as a linear combination of the energy eigenstate. So if psi n are the energy eigenstates, and this is a linear combination, then the probability, that if I make a measurement and I get the value En will be given by Cn squared. Okay. The first thing I wanted to say is that, if say psi 1 and psi 2 are eigenstates of an operator, belonging to two different eigenvalues. I should say a Hermitian operator or a self-adjoint operator. So I'm going to use the two words almost interchangeably. A self-adjoint operator. Say two different eigenvalues, say alpha 1 and alpha 2. Then the inner product between psi 1 and psi 2 is going to be 0. Okay. So eigenvalues, eigenstates belonging to different eigenstates belonging to two different eigenvalues are orthogonal. Okay. There's some subtleties there which has to do with degeneracy, but I won't go into that in this course. Okay, Farhan, does this cover what your questions or?
Yes, sir. Understood.
Okay. Okay. All right. Anybody else has any questions, say, from the previous time?